Our next speaker will be Dr. Mark Silberstein, who is working as an associate professor at Technion, Israel Institute of Technologies. He is the head of the Accelerated Computer Systems Lab, where the team is using bleeding-edge technology to build new, easy-to-program, high-performance systems with strong security. Their research covers a broad range of computer system topics, including operating systems and program extractions for emerging hardware, data center scale operating systems, new defenses against hardware attacks, new compilers and runtimes for secure processing, and much more. In 2020, Dr. Silberstein received the Jochen Liedtke Young Research Award from ACM's Eurosys. And in his talk today, he will describe the ongoing efforts in his lab to build an accelerator-centric operating system called OmniX. Over to you.
Thank you. I'm just checking that you can hear me.
Works well. Also, we can see your screen.
That's perfect. Okay, great. So I'm thrilled to present our work here. Thank you very much for inviting me to speak at this great event. So just a brief introduction to what we're doing in the lab. Indeed, you already mentioned some of it. You're very welcome to visit our webpage where we describe all our activities, all our projects in detail, including publication, references, etc. So this is actually one of the, this talk is going to be about one of the topics, one of the pillars of our lab, accelerated centric operating systems. So let me jump right to it. So it's kind of an interesting that I did not coordinate this slide with the previous speaker. But it turns out that, you know, this is exactly the question that he finished his great talk, which is, you know, what would be the timeline for this revolutionary technologies, and to what extent there will be a disruption to the computing stack. And the truth is that, as you can see here, the more you go to the right, the more the computing stack that is presented on the left will be disrupted. And this is not my slide. This is a slide from a great presentation done a few years ago. It's called IEEE Rebooting Computing Conference, and it was discussing exactly that question. So what we can infer from this slide is that it's likely that the future disruptive technology will take time to actually be adopted. And so what we're having here, due to the slowdown of the combination of Moore's law and other various laws that basically make the performance of the computing system grow slower than we used to. So this is the picture that we might see if we, you know, schematically consider how the performance is going to look like in the near future, where today we kind of reached the plateau, and this plateau is going to continue with the existing technology. So the new technology that is going to take off in the near future or in the further future is going to cross into with the existing technology sometime, and indeed the maturity of that technology is not going to happen very, very soon. So what the real question that we should be asking ourselves is, like, what are we going to do by then? And so the solution, or to some extent the temporary solution for us, temporary meaning next 10 years, I think, is hardware specialization and near data accelerators. What it means is that we're not going to talk today about a complete disruption of the computing stack. Rather, we are going to talk about the evolution or more efficient use of existing transistors and existing technologies in order to achieve the performance benefits that we're all looking for. So if we take a look at the computer hardware today, and we look at how modern servers are built, we are already seeing that quite a lot of silicon or transistors, in other words, are spent on peripherals, on accelerators that are outside of the standard CPU. And so what we're really seeing in recent years is that all those accelerators are becoming programmable. And that means that your program that you're going to run on the computer of the future, or basically the computer today, is not going to be running only on the central CPU, but also is going to be running on the network accelerator and storage accelerator and GPU parallel accelerator. And the result of this is that CPU processing unit is no longer central. It's no longer a central processing unit. It is just a controller that dispatches computations to all those accelerators. And we would call those accelerators X processing units, so XPUs, for the lack of better letter, that can just as a template serve as a template for various kinds of processing units that GPUs, TPUs, and all other PUs. And so this is the world that we live in today. Now, interestingly, the servers that are already becoming distributed, as I mentioned before, they are becoming literally distributed in data centers. In today's data centers, for the sake of getting high TCO, lower TCO, I'm sorry, for the sake of getting lower TCO, though the accelerators get distributed in what is called the disaggregation architecture. Disaggregated architecture is the one where processors and accelerators and storage are distributed are pooled together, and then this allows us to connect them through the network and build perfectly suited systems with just enough resources and with high enough utilization, such that these shared pools of resources are used to allow improvement in utilization. All of those are apparently connected through very high-speed networks. Now, again, here we are seeing that the system that is being used in data centers and is increasingly deployed in existing systems today, this is a distributed system, not a single node system that we got used to. Only that all those different parts of the system are different processors, or heterogeneous processors and storage. So the question is, how do we program all those, right? So on the one hand, we can work with existing technologies and work properly as we got used to. However, this will not give us the performance advantages. I will talk about it later in the talk. And so the programmability wall is this wall that we're all hitting as programmers, as software developers, where we have to work our ways through the complexity of the system and yet get correct programs with high performance. What happens is that the more processors you have, the more different types of processors you have in the system, the harder it becomes, exponentially harder it becomes to program. And as a result, the number of skillful developers is also dropping. So this is the real problem of today's system: how to integrate all those pieces that each one of them are extremely efficient at particular tasks that they're doing. But in order to build a real high performance application, you have to work very, very hard to get all those pieces together. The result of not being able to do that is that the hardware becomes underutilized, the applications suffer from low performance, despite the fact that individual components are fast. The efficiency is low and the costs are apparently much higher than expected because a lot of resources are wasted. And this is the sad result of the existing systems. You cannot program them correctly at the same time maintaining efficiency. So in the talk, in the remainder of this talk, I'm going to talk about the root cause of the programmability wall. And as the title of the talk is hinting, it's going to be about operating system design and new architecture of an operating system, which we call Omnix. So I'm going to talk about the principles of that operating system. I'm going to talk about the examples that we developed during our project. And I will also discuss the application of Omnix to disaggregated systems, showing that the concepts are becoming even more true in the systems of the near future. So in order to kind of drive home the real problem that we are all witnessing today in systems and why it is so hard to program them, let me consider a very simple application. This application is you can think about an image server like Flickr or Facebook, where you upload your photos and those photos get enhanced and stored. And then whenever you want to access those photos, the specific photos that you're accessing will be retrieved, then resized to the right form factor, to the right scale to fit the screen, and then eventually received by your phone or laptop. And so what I'm going to talk about is how people might want to build those servers with the accelerated devices that we have. So let's assume I have a server that already includes a NIC with an accelerator and network card, right? An SSD, a storage device with a processor that can run software, and the GPU that can also do some stuff. Apparently, there will be also CPU. So let's take one of those functions and let's map it onto this server. So let's take a look at, for example, number 2. Whenever you're retrieving a data from the server, you would want to accelerate the network processing on the NIC. For example, parsing the request. You would want to resize the data inside the storage and then store some kind of cached version of that resized image, and then eventually pass it back to the NIC. And for the put, for storing the image, you would imagine having a GPU enhancing the image quality, and then again storing that image in SSD. So something important happened here. We actually built, or we want to build, a system where the CPU is not really used at all. That is because we have all those near data processing devices. We have NIC, SSD, and GPU that are specialized and purpose-built for those tasks. So you would imagine that you can just throw the CPU out and live with it. Unfortunately, this is true only on the paper. What you would really want to do is to write a program that runs on all of these systems, and this program should be implemented somehow with existing programming language. So you imagine you would have a function that runs on the NIC that parses the request, and then a function that runs on the storage device that resizes the image, and then going back to the NIC and then sends the results. So this is all The question is how would you approach this problem to implement this very, very efficient server on these two devices. So what you would do, you would use the standard set of operating system calls like receive and read and write and send. I hope that the meaning is clear here, what you want to do with these calls, but all of those will be running on the CPU because those calls are implemented by the operating system, and this operating system, the only place that is located is CPU. And that means that if you do want to implement this very nice example, what you would end up having is that all the data would be first received by the CPU and then sent back to the NIC just to do the parsing, in which case the next stage would be again reading a file, which would again be implemented by the CPU. And so you already understand where I'm heading. You see that the whole efficiency of the system basically is nowhere near what we expected to have with those near data processing devices. So we're going to spend a lot of time implementing basically running this application on good old CPU just in order to pass data around and invoke all those devices. And again, the real problem here is that those devices do not run anything that resembles the operating system that one can use. And as a result, all those abstractions that we got used to are not going to be available on those devices. And the only place that they will be available and can be used is the CPU. So you can see that this architecture that we imagine, the one where we would use all those specialized processors and all those specialized devices, is actually not viable with programming systems today, with software systems. And the real root cause of it is that the CPU is the only one that runs the operating system. It is right in the middle, and everything goes through it. As a matter of fact, this example is just a toy example, but you can imagine that the same examples are also true for a variety of real systems which can be using training processing units or inference processing units or whatever you imagine and think about. All of those will end up doing exactly the same thing, looking exactly the same way. The problem is that our operating system architecture is CPU centric. And this problem impedes the whole efficient use of these heterogeneous systems today. So what I'm going to talk about today more is about the solution to this problem. And this is Omnix, an accelerator-centric operating system architecture that allows us to run operating system abstractions directly on accelerators. And it basically creates this decentralized distributed environment where all those accelerators and all those units can talk to each other directly without having to use the CPU in the middle. And that, as we will see, will allow a much simpler programming and much more efficient programming. I should note that there is this trade-off between the simplicity of programming and the efficiency, that the higher the performance of the program that you have, or the more you have to spend on optimizing it. Our goal is to reduce the effort that you have to spend on optimizing, offering the operating system that is already doing that for you. So the way the program in Omnix would look like is this. You would basically invoke a flow graph, a task graph of tasks that would run in each one of those devices and would pass over data between the NIC and the storage directly without going through the CPU. All right, so how do we do that? Is it even realistic? Is it a vision that might be possible to realize in 10 years, or it is something that is available today? Well, the answer is a little bit more complicated than whether it's one or another. It's somewhere in between. Some of these ideas can be implemented today, as I will show, and some of them are sort of in a transition point where the hardware is slowly going to allow building this kind of architecture. And we believe that in really short term, we will see more and more hardware that will do exactly that. So, okay, so let me kind of lay out the basic things that that characterize this kind of accelerator-centric operating system. So when we're talking about operating system, we tend to think about Linux or Windows or Android. But the truth is that the operating system is this puzzle that is built out of a lot of small pieces, and there are some core pieces around which you build the operating system. But fundamentally, operating system is a set of services. And when I'm talking about operating system for accelerators or accelerator-centric operating systems, I'm talking about those services individually. Together, after I build a whole lot of those services, I can say that I can develop a complete application in a complete operating system. So let's talk about the types of services in this operating system. One type is accelerator-centric. Those services are running on accelerators themselves, and they allow the accelerators to access all other accelerators and CPUs in the system. Then there are accelerator-friendly services, and those services are such that they are targeting accelerators that cannot run user code, but you still want to optimize the operating system so that they can work, so that the other accelerators or the CPU would be able to work efficiently with those kind of accelerators. And last, data-centric are the type of accelerators that do not require any CPU at all. And those require different types of abstractions, which we call inline near data processing. So I will talk about those. Just for a quick reference, as I mentioned earlier, the operating system, in our view, is a set of services. So during the years, we developed a whole lot of these services that basically demonstrated the viability of the concept, but to some extent, we have never built a complete coherent operating system for a single server. What we did do, we did build a complete operating system for data center, which I will talk briefly later, that really follows the same ideas, the same concepts. So let me briefly give you a few kind of examples of what we came up during these years. So let's talk first about the GPU, which is the accelerator that we all know and love because it does machine learning really quickly and deep learning. And so let's talk about the GPU being able to access network and storage directly without having to go through the CPU. The very first system that we built was a GPU file system. This is not a real file system. It's just an interface to a file system that is located on the host, but it allows one to access files directly from GPU, and it does so by exposing the same shared namespace. Essentially, what it means is that you can run your GPU program and just access files as if you were running it on the CPU. Another idea that kind of followed the line of GPUFS was GPUNet. This is a network library, implying that what you can run is a complete server fully deployed on GPU without having to the CPU at all. And importantly, these servers allowed both, basically, this API allowed both to run both the client and the server on the GPU. And let me briefly show the kind of application that we can support. But before that, kind of a summary of what those two systems demonstrated. Those two systems showed that accelerators can be in full control over all of its I/O, meaning files and networking can be all fully done without leaving the GPU kernel, this function that runs on the GPU. it allowed a whole bunch of different applications to be developed, those applications that would have been much slower if you were not to use our infrastructure. And this points exactly in the same direction as I mentioned earlier. The optimization task is sometimes so tedious that that the acceleration that you can get from accelerators basically becomes unused because of the inefficiency of interaction with them. And GPUNet and GPUFS helped us out of this. So let me show you one specific application as promised. This is the application that tries to identify or verify the identity of a person that, let's say, presents himself and herself in a border control, and you present your passport and your name and your photo, and then the system looks up for your photo in the database and compares your biometric characteristics from the server with your actual name and whatever is written in your passport. So this is what we call face verification. You can imagine that the verification of the face is a tedious task. So you might want to use GPU for that. And what we show here is that you can build such a system by using GPUNet without having to use CPU in the server at all. And this result shows that GPUNet on a single GPU achieves 2x throughput compared to 6 cores of a CPU, and with half of the code and 1/3 of latency. What is really important is that, as I mentioned, the GPU used without GPUNet would be really inefficient for that same task, just proving to what extent this kind of integrative effort of the operating system optimizations is necessary and useful. The key to all those is to hide the interaction between different components in the system, and those are hidden under the hood and optimized with this with some of the recent capabilities offered in modern servers that are called peer-to-peer DMA. This functionality allows one to transparently move data between the peripherals without going through the CPU. As I said, using this feature is difficult, and GPUNet and GPUFS allow one to use them completely automatically, transparently. So far, we talked about accelerating operating system services and the examples that they simplify code development. But what if one cannot add code to an accelerator and cannot run an operating system? What would be the way to still allow accelerators to more efficiently use the rest of the devices? So the key here is to make the host operating system accelerator aware, something that we are seeing today more and more. And this work that I'm showing now is the precursor of the NVIDIA's GPU storage or Storage Direct project. And so here, what we offered in this project is to allow one to move to move data to the GPU by using standard file system abstractions, just read and write, but by using GPU memory as the buffer. This achieved really significant speed up, but what's more important, it was completely transparent for the user. So the question that I'm going to ask now is that, okay, so we talked about accelerator-centric services, we talked about accelerator-aware operating system services, but can we actually completely drop the CPU from the system and still achieve a programmable and efficient system? Well, it turns out that the answer is yes, and what we are showing this line of research is that there are a lot of different systems and a lot of different infrastructures that one can build, to achieve exactly that. And the result of it is much lower latency, much better scalability, and much lower costs that you need to build such systems. So do you really not need CPU here? The answer is that you do not need the CPU in the control path and slow path. In the fast path, I'm sorry. You don't need the CPU in data path, but you do need the CPU in control and in control path and slow path in order to set up all the system. Once the system is set up, the CPU is no longer taking part in it. So let me show you one example. Again, as I mentioned, we have several systems that demonstrate this concept. The one more recent example is called Lynx. So the idea here is that we want to take a server that is doing things like neural network inference, and we want to we should have, make it more efficient. We want to make it more efficient by realizing that most of the application-specific logic is running on an accelerator and GPU usually, but the rest is not really doing anything smart, meaning that most of the application part that is running on such servers is entirely generic. Okay, so this is the server that accepts some kind of requests. For example, neural network inference, as I mentioned, performs the inference by offloading the request processing to the accelerator and then getting the results back to the client. And so we asked ourselves, are there more efficient ways of building such servers? And the answer is that we can completely remove the central processing unit, the CPU, from such systems or powerful CPUs and replace them with wimpy CPUs that are available on SmartNICs. As a matter of fact, those do not need to be even CPUs, they can be FPGAs that can be used to perform all the network processing, but the rest is entirely done by the accelerator, and the CPU is not part of the game. So we built the system with existing hardware, and we implemented it both on FPGAs and on ARM-based BlueField NICs, as well as on NVIDIA GPUs and visual computer accelerators, VCAs. And what we are showing here is that in this architecture, you can achieve scaling of your system, linear scaling, up to about 100 accelerators served by a single NIC, SmartNIC. What the architecture on the right shows that this SmartNIC can manage both the local GPUs as well as remote GPUs by means of RDMA NICs. What is really important about it is that think about how much cost you can save and how more efficiency you can gain out of the system by replacing I would call it 10, 15, 20 CPUs with a single wimpy SmartNIC. This result is definitely something that we're going to see adopted in industry, maybe in a couple of years or 3 years from now. So I talked about the single server so far. Only the last slide mentioned somehow this disaggregation topic with remote access to accelerators. But fundamentally, the whole discussion has been so far about single machine. However, as I mentioned, in future systems, there will be no single machines per se. We will see a bunch of racks that one will host all the CPUs, one will host all the GPUs, SSDs, and etc. And those will be connected through the network. And what is really important here is that this is the way people intend to achieve efficiency in data centers. Will Omnics ideas apply in this system? The answer is definitely yes, and let me show you how. So the accelerators, the server-centric design that we are all using is the one where the operating system runs on the CPU and CPU is connected to all the peripherals. In practice, however, all the devices in disaggregated data center will be spread over the data center. And so all the interactions with the same CPU will all be through the network. However, the operating system will not be aware, at least today, it is not aware of the fact that all those devices are remote, implying that whatever you're going to run today on this system is going to perform all those very inefficient interactions over the network with all those devices. And this is really bad. This is definitely not what you want, because this is going to reduce your performance substantially. Surprise, surprise, Omnix ideas really apply here, because the problem is the same problem, although the environment is different. We have an operating system architecture that is CPU-centric, and we really need to distribute it across all different devices. What it means is that what you can build is a distributed system, what we call disaggregation native operating system. This is a paper that we have published just recently. And this one talks about running an operating system in SmartNICs and controlling all those devices from the SmartNICs without involving the CPU, whereas the CPU is just a, you might call it sequential accelerator, or accelerator of sequential tasks. So in the same application, as I mentioned, one would not have to use the CPU, the centralized CPU. One would build the distributed system where the all different parts of the system will communicate directly with each other without having to go through the single location. So in fact, this is a distributed operating system, only that it is running in Wimpy processors, and thus is very, very efficient. So just to, I'm almost done with the talk, so let me just go to the conclusion. The future systems will be omniprogrammable. They are already omniprogrammable, as a matter of fact. They are heterogeneous, and they are disaggregated in data centers. And so we're all facing a programmability wall, making it really, really hard to program those. The accelerator-centric operating system architecture is the one that can improve both performance and programmability at once. And this is to some extent, the initial stages of a complete revolution of how operating system design should look like and will look like. So this operating system abstraction, this operating system architecture is exposing OS abstractions to accelerators to all those parts. It tightly integrates new abstractions with host OS, and basically makes it much easier for you to develop applications. It is applicable today, and even more so in the near future. I should mention that a lot of parts of what I've already said is implemented and available on our GitHub. And last but not least, I have a great group of really talented people who are helping me and basically pushing everything. Well, I'm helping them, as a matter of fact, to do all this nice stuff. And at this point, I'm done, and I will be happy to take questions.
Thank you so much. Very insightful. Also very interesting to have another aspect and perspective how we should focus less on the CPU and more on the things around it. There are a few questions. I have tons of questions, but let's look at the QA questions first. Would coherent memory between accelerators and processor address the offloading overheads? I think this was a question, especially from the beginning of your talk.
Right. So this is a very good question. It seems that coherence is the nice programming abstractions, but abstraction or nice way of simplifying operation, but does not necessarily reduce overheads. You can think, for example, about NUMA systems, non-uniform memory access systems, that are already cache coherent. And those need to be optimized for. So cache coherence is just convenience. It's not necessarily something that helps your performance.
Right. It will only get us this far. Another question is, does this mean that the consumers of this OS need to be aware of the ordering or connectivity between the various XPUs?
That's a great question. It very much depends. I don't think that the operating system itself should be the one that would dictate that. So it very much depends on the environment. For the environment of a single server, where the connectivity is really, really fast and there is more control on network, which is PCIe, I believe that it will be all transparent for the user where and what is connected and which order. However, on the other hand, the larger the scale of the system, the more things can get wrong in the network, and so you might need to spend more time in figuring out how to do that. Whether it can be made transparent or not, that's an interesting question, but I can't really say, I think.
Thank you. Last question from the Q&A. Wondering if the shared memory-based communication within an accelerator be a bottleneck for this kind of approach. Please share your thought on this when we are solving a large-scale optimization program.
Well, I think that this is, to an extent, an orthogonal question to the vision that I presented. In a sense, an operating system is there only to help you integrate things together, right? And it does not necessarily, it is not something that helps you program your high performance computing system in a sense that you would still have to use like MPI or CUDA or whatever. The high performance systems are much more targeted toward a single application. And so in this case, your programming environment, your library that will help you with message passing and being that shared memory or not, that's a programming model that you decide to write in as your application. However, if you have a lot of different applications, like in servers, right, you have a lot of different pieces that cooperate together to build one single system. In that case, this is where your operating system becomes really important, and that is why you can even think. Okay, let me give you another analogy. When you're running an MPI program, do you know anything about your operating system? I don't think that you do, right? Because everything is done, most of the things are done directly by the user, because usually it is trying to squeeze out the last bit of performance out of your communication and whatnot. Operating system is usually only interfering with the operating system scheduling noise and whatnot. So the high performance environment is almost by definition very different from the server environment that I was talking about. And in server environment, there are a lot of third-party components that you really want to play well together. And the only thing that does this gluing of these things together is the operating system. And the reason why we haven't been able to build those nice systems so far is exactly because the operating system lagged behind in terms of the abstraction and optimization that it allowed. So it is immensely difficult today to build anything accelerated in the scale of a high performance application, but for the servers, right? And so what we are trying to say is that, hey, we need to change the operating system such that whenever you will want to build this large scale servers and really efficient servers, it will be easier for you to do rather than struggle through all these connecting all these different components. And that is the key of what we are doing. This is our goal.
Thank you. I think we are out of time for this slot, but thanks for taking the time to answer the question. Thank you for your talk. I think there's some more questions coming in. Maybe you can have a look in the Q&A.
Sure.
We will take a short break now, so everybody can get a drink and stand up for a second. And we come back at 5:20. Thank you, everyone.